Welcome to this rigorous scientific lecture on the Meissner effect. Today we're going to explore one of the most profound discoveries in condensed matter physics, the experimental confirmation that superconductivity is fundamentally different from perfect conductivity. In 1911, Kamerlingh onnes discovered superconductivity when he observed that Mercury's resistance dropped to zero below 4.2 Kelvin. Initially, physicists thought superconductivity was simply perfect conductivity, but was this the complete picture? Let me pose a critical question. If a material is just a perfect conductor with zero resistance, what should happen to magnetic fields when you cool it below the transition temperature? According to Faraday's law of induction, the answer is that magnetic fields should be frozen inside the material. Any change in magnetic flux would induce currents that oppose the change, preserving the original field. Let's begin our experimental workflow. Step 1 is to measure the magnetic response of a material above its critical temperature. We start with a sample at room temperature in an applied magnetic field. Here we have our sample above the critical temperature, Tc. We apply an external magnetic field B. The field lines pass straight through the material because it's in the normal state. The material is paramagnetic or diamagnetic with a very small susceptibility. Above the critical temperature, the material behaves as a normal conductor. Magnetic field penetrates the entire volume. Now let's perform our first critical experiment, zero field cooling. We remove the external field, then cool the sample below the critical temperature, then reapply the field. The zero field cooling protocol has 3 steps. First, we turn off the external magnetic field. Second, we cool the sample below T circa. Third, we turn the field back on. Observation. When we reapply the field below Tc, something remarkable happens. The magnetic field is completely expelled from the interior of the superconductor. The field lines bend around the sample. This is the Meissner effect. Inside the superconductor, the magnetic field B equals 0. Complete expulsion. Now comes the critical experiment that distinguishes superconductors from perfect conductors. We perform field cooling, apply the field first, then cool below Tc while maintaining the field. In field cooling, we keep the external magnetic field on during the entire cooling process. This is the key test. If the material were just a perfect conductor, Faraday's law tells us the magnetic flux should be frozen into the material. The field should remain trapped inside. Here's the stunning result. A perfect conductor on the left traps the magnetic field inside, but the superconductor on the right expels the field even during field cooling. This is completely inconsistent with perfect conductivity alone. This observation is profound. It proves that superconductivity is a distinct thermodynamic phase of matter, characterized by perfect diamagnetism, not merely a state of zero electrical resistance. Let's quantify this effect mathematically. We need to introduce the magnetic susceptibility chi and understand perfect diamagnetism. The magnetization M equals chi times the magnetic field intensity H. Chi is the magnetic susceptibility. The magnetic flux density B equals mu0 times the quantity H plus M, which equals mu0 times 1 plus chi times H. For a superconductor exhibiting the Meissner effect, we require B equals 0 inside. This means 1 plus chi equals 0, so chi equals -1. Perfect diamagnetism. B inside equals 0 implies chi equals -1. This is the hallmark of the Meissner state. Let's do a quick back-of-the-envelope calculation. What surface current density is needed to screen out a typical magnetic field? Let's say we have an external field of 0.1 Tesla, which is about 1,000 times Earth's magnetic field. We want to calculate the surface current needed to screen this out. At the surface, the boundary condition gives us B0 equals mu0K, where K is the surface current density in amperes per meter. K equals B0 over mu0. Plugging in 0.1 Tesla and mu0 equals 4 pi times 10 to the -7, we get the current density. This gives us approximately 8 times 10 to the 4th amperes per meter. That's 80,000 amperes per meter of surface current needed to screen the field. This is an enormous current density, yet it flows without any dissipation whatsoever in the superconducting state. This is possible because of the zero resistance. The magnetic field doesn't drop discontinuously to zero at the surface. It penetrates a small distance, characterized by the London penetration depth lambda. The London penetration depth lambda L equals the square root of m over mu 0 nse squared, where m is the electron mass, ns is the superconducting carrier density, and E is the electron charge. Typical values of the London penetration depth range from about 50 to 500 nanometers depending on the material. This is the characteristic length scale over which the field decays exponentially into the superconductor. The magnetic field, as a function of depth x, decays as b of x equals b0 times e to the negative x over lambda L. Exponential decay. Here's a visualization. The external field arrows on the left penetrate only a distance lambda L into the superconductor. Deep inside, the field is completely screened to zero. Now let's map out how the penetration depth and the Meissner effect depend on temperature. This is crucial for validating the theory. As the temperature approaches the critical temperature Tc from below, the London penetration depth increases dramatically. It diverges at Tc. The temperature dependence is approximately lambda of T equals lambda of 0 over the square root of 1 minus the quantity T over Tc to the fourth power. This is an empirical formula that works well for many superconductors. Near the critical temperature, the superconducting carrier density decreases, so the field penetrates deeper. The Meissner effect weakens as we approach Tc. Here's an important question. What happens at exactly T equals Tc? At T equals Tc, the penetration depth becomes infinite. The superconducting state cannot sustain itself, and the material transitions to the normal conducting state. The phase transition is continuous for zero applied field. Let's discuss how we experimentally validate all of this. One powerful technique is alternating current susceptibility measurements. We apply a small oscillating magnetic field to the sample and measure the induced magnetic moment as a function of temperature. This directly probes the magnetic response. Here's a typical AC susceptibility versus temperature plot. Above Tc, Chi is nearly zero, the normal state. Below Tc, Chi drops sharply to -1, indicating perfect diamagnetism. The sharp transition at Tc is the signature of the superconducting phase transition. The sharp drop in susceptibility at Tc confirms the onset of the Meissner effect. This is direct experimental evidence that flux expulsion occurs precisely at the superconducting transition. An important refinement. Not all superconductors exhibit complete Meissner effect everywhere. We must distinguish between type 1 and type 2 superconductors. Type 1 superconductors exhibit complete Meissner effect and perfect diamagnetism up to a critical field H circa. Above Hc, superconductivity is destroyed abruptly. Type 2 superconductors have two critical fields. Between Hc1 and Hc2, they allow partial flux penetration and quantized vortices. This is called the mixed state, or vortex state. Type 1 superconductors on the left completely expel all flux. Type 2 superconductors on the right can allow flux penetration in the form of quantized vortices, each carrying one flux quantum. Each vortex carries exactly one flux quantum phi 0 equals h over 2e, which equals 2.07 times 10 to the negative 15 Weber. This is a fundamental quantum of magnetic flux. Most practical superconductors, including all high-temperature superconductors, are type 2. They can sustain much higher magnetic fields before losing superconductivity completely. Let's develop the theoretical framework. The London brothers proposed phenomenological equations in 1935 that explain the Meissner effect. The first London equation relates the supercurrent density, Js, to the vector, potential A, Js equals negative nse squared over m times A. Taking the curl gives us the second London equation. Del cross Js equals negative nse squared over m times B. This equation directly implies that currents flow to expel magnetic fields. When you combine the London equation with Ampere's law, you get a differential equation whose solution is exponential decay of the magnetic field with the London penetration depth. This naturally explains the Meissner effect. Let's calculate the critical current density that a superconductor can sustain before the superconducting state breaks down. Consider a cylindrical superconducting wire with radius r equals 1 millimeter. What's the maximum current it can carry? The magnetic field at the surface is B equals mu 0 I over 2 pi r. This must not exceed the critical field Hc, otherwise superconductivity is destroyed. Solving for the critical current, IC equals 2 pi rHc over mu 0. Let's use typical values. Critical field Hc equals 0.1 Tesla, radius r equals 1 millimeter, or 10 to the negative 3 meters. IC equals 2 pi times 10 to the negative 3 times 0.1 divided by 4 pi times 10 to the negative 7. This gives approximately 500 amperes. That's a substantial current for such a thin wire. How do we experimentally map the magnetic field penetration into a superconductor? Several sophisticated techniques exist. Muon spin rotation is an extremely sensitive technique. We implant spin-polarized muons into the sample. The muon spin precesses in the local magnetic field, allowing us to probe field distributions with nanometer resolution. Hall probe scanning microscopy uses a miniature Hall sensor to map the magnetic field just above the sample surface. We can visualize the Meissner effect and vortex structures directly. Superconducting quantum interference devices, or SQUIDs, are the most sensitive magnetometers ever created. They can detect magnetic flux changes as small as a single flux quantum, perfect for measuring magnetic susceptibility. Let's calculate the energy cost of expelling magnetic flux. This will help us understand the thermodynamics of the Meissner state. The magnetic field energy density is B squared over 2 mu 0. The total energy is the integral over volume. In the normal state, the magnetic field penetrates the entire volume 5 of the sample. The energy stored is B 0 squared over 2 mu 0 times V. In the Meissner state, the field is confined to a thin layer of thickness lambda L at the surface. The volume occupied by the field is roughly the surface area times lambda L. The energy difference is approximately B0 squared over 2 mu 0 times the surface area A times lambda L. This is the energy cost of maintaining the screening currents. Here's a profound question. Why does a superconductor willingly pay this extra magnetic energy cost to expel the field? The answer lies in the superconducting condensation energy. The energy gained by forming Cooper pairs and entering the superconducting state exceeds the energy cost of flux expulsion. This condensation energy density is approximately Bc squared over 2 mu 0, where Bc is related to the thermodynamic critical field. There's another fundamental length scale, the Ginzburg Landau coherence length 7. This is the characteristic size of a Cooper pair. The coherence length xi is roughly h bar versus f over delta, where versus f is the Fermi velocity and delta is the superconducting gap, typically tens to hundreds of nanometers. The dimensionless ratio kappa equals lambda over xi is called the Ginzburg-Landau parameter. This ratio determines whether a superconductor is type 1 or type 2. If kappa is less than 1 over the square root of 2, approximately 0.7, the material is type 1. If kappa is greater than 1 over root 2, the material is type 2 and can form vortices. The physical interpretation is elegant. Kappa represents the competition between the magnetic screening length lambda and the Cooper pair size xi. When lambda dominates, flux expulsion is costly and vortices form. When xi dominates, complete flux expulsion wins. The Meissner effect was discovered in 1933 by Walter Meissner and Robert Ochsenfeld, more than 20 years after the discovery of superconductivity. This discovery was revolutionary. It showed that superconductivity is not just a transport phenomenon of zero resistance, but a true equilibrium thermodynamic phase with unique magnetic properties. The Meissner effect inspired the London brothers to develop their phenomenological theory in 1935. Later, it was one of the key facts that the BCS microscopic theory had to explain when Bardeen, Cooper, and Schrieffer developed their theory in 1957. The Meissner effect has spectacular practical applications, most famously magnetic levitation. A superconductor cooled below its critical temperature will levitate above a magnet. The magnetic field from the permanent magnet is expelled by the superconductor, creating a repulsive force that can support the weight of the superconductor. Maglev trains exploit this effect. Superconducting magnets on the train interact with guideway coils to produce both levitation and propulsion, enabling speeds over 600 kilometers per hour with minimal friction. Let me summarize the key conclusions from our rigorous analysis of the Meissner effect. First, perfect conductivity by itself, based on classical electromagnetism and Faraday's law, predicts that magnetic flux should be frozen into the material, not expelled. This is the crucial distinction. Second, the Meissner effect demonstrates perfect diamagnetism with susceptibility chi equals -1. This is a thermodynamic property, independent of how the superconducting state was reached. Third, field cooling and zero field cooling give identical magnetic states below Tc. This proves superconductivity is an equilibrium thermodynamic phase, not a kinetic phenomenon. Fourth, the London penetration depth lambda L, typically 50 to 500 nanometers, sets the characteristic length scale for magnetic field screening. Fifth, the temperature dependence of the penetration depth, diverging as T approaches Tc, confirms the continuous phase transition between normal and superconducting states. Sixth, the Ginzburg-Landau parameter kappa equals lambda over xi distinguishes type 1 superconductors with complete Meissner effect from type 2 superconductors that allow quantized vortices. In conclusion, the Meissner effect is the magnetic signature of superconductivity. It elevates superconductivity from a mere electrical transport phenomenon to a fundamental thermodynamic phase of matter. It reveals that superconductors spontaneously break electromagnetic gauge symmetry and expel magnetic fields through macroscopic quantum coherence. This discovery remains one of the most beautiful confirmations that nature exhibits emergent phenomena fundamentally different from our classical intuitions. The Meissner effect is not just an interesting property of superconductors, it is the defining feature that distinguishes true superconductivity from perfect conductivity.